Hi, everyone. Can you hear me fine? It's such a thrill to welcome everyone to the 7th Roger That Conference, a celebration of space exploration in honor of Roger B. Chaffee, astronaut and a native Grand Rapidian. Our tagline is "There's enough space for everyone," and the aim of this conference is to bring space enthusiasts in all forms and from all parts of the world together. So without any more chit-chat, let's get to it. Our first guest is the incredible Dr. Burçin Mutlu-Pakdil. Dr. Pakdil has a bachelor's in physics from the prestigious Bilkent University in Turkey, followed by a master's degree from Texas Tech in Lubbock. She received her PhD in astrophysics from the University of Minnesota in the Twin Cities. She spent 3 years of postdoctoral research at the University of Arizona and then 2 more years at the University of Chicago. Currently, she is the assistant professor of physics and astronomy at Dartmouth College, and her research focuses on characterizing the smallest and faintest galaxies in the universe and studying the role of dark matter in their formation. So take it away, Dr. Mutlu-Pakdil.
Thank you so much. And first, I need screen sharing. It is disabled currently. Okay, I think it will work now.
Yeah, you should have it now.
Okay. Okay. Let me see. Okay, I am setting up my screen. Okay. Hi, everyone. Thank you so much for having me. I am an observational astronomer, and I study galaxies, and I especially am interested in extreme galaxies so that we can understand how galaxies form and evolve. And today I will talk about, now we are living in a very exciting era of deep and wide field surveys, and these surveys are changing the field with new discoveries. They are discovering the faintest and smallest galaxies, and basically changing our idea of how galaxies form and evolve. And today I will quickly mention the current state of the field and how these extreme galaxies are changing our field. So I will quickly, this is my outline of the talk. So first I will give some introduction and some motivation why we study these systems. And then I will share our observational efforts to find these extreme galaxies around the Milky Way and beyond the Milky Way. And then finally, I will conclude with the future prospects. So let's start. Galaxies are generally perceived as giant systems, right? This is a picture of a galaxy, M101, and this is like Milky Way, and it has billions of stars, but vast majority of galaxies are actually dwarf galaxies, and they can only harbor a few thousand or even a few hundred stars. The most famous ones are our neighbors, large and small Magellanic Clouds. They are actually small, but close enough and bright enough that we can see them with the naked eye from southern hemisphere.
Dr. Pakdil, sorry, I'm going to interrupt you. Your slides are skipping a little. They keep skipping back and forth. So I'm not sure. I don't think that's at our end, but I didn't.
That is so strange. I am seeing the.
Sometimes they keep going back and forth. Okay, now this is working. So if you want to keep it on this, I think this will work.
Okay, then I will keep this way.
Thank you. Sorry for interrupting you. Thank you.
No worries at all. So the most famous one is our neighbor around which is visible to the naked eye, and we can, when we look at the sky, we see them as smudges like this. And here is the Milky Way stars. Milky Way star looks like a band of stars because we are within the Milky Way and we are looking at the disk of the Milky Way. So to put this into perspective, here is the relative sizes. So this galaxy shape represents the size of our galaxy, represents the size of our galaxy, Milky Way. And you can see the large and small Magellanic Clouds compared to the Milky Way, and you can see how tiny they are relative to our own galaxy. And just a point, just a fun fact, of course, we are not at the center of Milky Way. We are at one of the arms of the spiral arms. Okay, although they look very small compared to Milky Way, large and small Magellanic Clouds are not the faintest ones. Leo 2 is another Milky Way satellite galaxy, dwarf galaxy, and it is 15,000 times smaller than fainter than Milky Way. And now you can see individual stars concentrated at the center, right? It's very different than the images that we are used to. And we can go even fainter. And here, this is Draco. This is 40,000 times fainter than Milky Way. Now it is getting harder to identify galaxy in the images. But if you look at it carefully compared to the side fields, the center, we can see individual stars concentrated here. So Draco was in fact the faintest galaxy known for 40 years. But then we have better images with better sky coverages, and now we started discovering galaxies that are much, much, much fainter than Draco. So this is the exciting timeline of Milky Way dwarf discoveries. So here in x-axis we have a year, and in y we have the total number of dwarf galaxies, non-dwarf galaxies at that year. So as you can see, early 2000, we only knew about dozen dwarf galaxies. And then Sloan Digital Sky Survey happened and doubled the number. We'd start discovering things. And then Dark Energy Survey happened and we found many more. And with better images of sky, with better sky coverages, now this number reaches about 60. And recently discovered ones are much, much fainter than the previously known ones. And we call to differentiate the distinction, how the faint nature of these systems, we are calling the recently discovered ones ultra faint dwarfs and the previous ones classical dwarfs. And guess what? We started to discover galaxies that are fainter than a single bright star like Betelgeuse. So this is an example of such galaxy. This is Willman 1. And can you see a galaxy here? It's not the screen. It's not the your eye. It is the galaxy. You cannot see it. It has only a few hundred stars. It is 10 million times fainter than Milky Way. And because of the faint nature of its stars and the number of stars, it is basically invisible in the images. And we are now discovering these very extremely faint galaxies. And I am one of the many researchers who are trying to find these extremely faint things in new observations. But you can ask why we should care, why we are working so hard to find these basically invisible galaxies. Because they might be the key to answer some of the biggest questions in astronomy. We now know that universe is more than what we can see. Only a 15% of total mass in the universe is normal matter that we can observe, like galaxies, planets, stars, dust, you and me. We are all normal matter, and we are like, it's only 15% of matter is normal matter, and everything else is mysterious matter we call dark matter, and we cannot observe it, but we know it is there because we see its effects in normal matter. So what is the nature of dark matter? Well, we don't know. But we have so many ideas what it could be, right? About its size, its speed, its interactions with the other materials, matters. But now, since we have all these ideas, what it could be, now it is time to test these amazing ideas. And guess what? Dwarf galaxies are the best place to test these ideas, because dwarf galaxies are not only faint and small, they are also the most dark matter dominated systems in the universe. So here in this plot, I'm showing you, here is the luminosity. So with the arrow towards this side, the objects are getting brighter, and the here in y-axis we are looking at the total ratio of total mass to the visible mass.
Going back off.
So here, as you can clearly see, dwarf galaxies clearly dominated by something other than their stars. So they are the most dark matter dominated systems in the that we know of in the universe. And also, to test our ideas, we generally create these digital universes. And this is a digital universe. And it is in this universe, we are just using dark matter. We are not including normal matter. And everything that you see here is the density of dark matter. And what we are looking at is a dark matter clump that will create a Milky Way-like system at the center. And so we hear this clump of dark matter, we call it dark matter halo. At the center, the densest dark matter region creates a galaxy, Milky Way-like galaxy. And you can see still within the dark matter halo, there are several dark matter clumps, right? And this is where dwarf galaxies form. These subhalos is where dwarf galaxies will form. And interestingly, different dark matter models, different dark matter theories predict very different things for these subhalos that will form dwarf galaxies. For example, one of the most promising dark matter theory is called dark matter. And here the cold doesn't refer to temperature, it refers to how the speed of the particle, basically, how fast the speed of how fast the dark matter particles move. So in cold dark matter model compared to the warm dark matter model, the subhalos, we see much more subhalos. They are much dense, and warm dark matter just predicts fewer subhalos, meaning it predicts fewer dwarf galaxies. So that's great. Then what I can do is just look at the a certain region on the sky and count the number of dwarf galaxies and compare with the theories, right? And then decide which theory is predicting correctly. But we have a problem in this thing, in this logic, because we don't know. We know that moderate size of the subhalo will create a dwarf galaxy. But we don't know for the smallest one, which one of these will form stars. So for dwarf galaxy, so for dark matter halo to create galaxies, it needs to be a certain size. So it should be able to cool gas and form stars, and then they can be visible as galaxies. So we don't know which one, what is the threshold of the galaxies for example, in this one, this is for cold dark matter model, but what we are seeing is dark matter halo mass and dark matter halo abundance, and this is the prediction. As you can see, smaller the mass is and more abundance it has, and we know the faintest mass, they cannot create dwarf they cannot form stars, so they cannot become galaxies. And we know certain size dwarf subhalos, dark matter subhalos, will create dwarf galaxies. So we observe them, but what we don't know is this region, transitional region, right? So by discovering and studying the faintest dwarf galaxies, we can indeed constrain this region. We can indeed learn about the lower limit to the galaxy formation. Okay, in addition to this, there is another problem. So far, the digital universes that I mentioned only included dark matter, but in real universe, we also have normal matter, right? So when we are talking about, when we comparing digital universe to observed universe, if you just consider pure dark matter simulations, we are not comparing apple to apple, we are comparing apples to oranges, right? So what we need is we need normal matter physics in our simulations. And luckily now we are creating more realistic simulations, and we can actually start comparing these. Here is a digital universe again, and here we are seeing dark matter component, and we are seeing the star, a normal matter component. As we just said, at the densest dark matter region, we have galaxy, and in the subhalos, the clumps, we see dwarf galaxies. And it turns out that in addition to nature of dark matter, all these small structures, dwarf galaxies, are also sensitive to the tidal effects from normal matter. So these galaxies at the center can actually destroy some of the faintest galaxies. So we need to be careful about the interpretations and comparisons. So then the test becomes disentangling the effect of dark matter and normal matter, right? Because the dark matter particles will affect the number of dwarf galaxy subhalos. The threshold will affect which subhalos will turn into galaxies, and normal matter, some of the normal matters can also disrupt the smallest structures. So we have a complex problem in hand, and we need to be able to disentangle all these effects. And also, I will say that this is a digital universe again, and at the center there's a Milky Way mass galaxy, and here these are the dwarf galaxies. They are because of the gravitational effects, they are like moving around, they are collapsing, their stars pulled apart because of the tidal interactions. And you can see some of them are creating actually like stream-like structures, and these structures actually can survive for a long time and can act as a fossilized remnant of galaxy formation. So what we can do now, since we have more realistic simulations, we can actually now look at this volume, right, in the real universe, look at this certain volume, a nearby galaxy and surrounding, and just count the dwarf galaxies around it, and some of these stream-like structures, these tidally destroyed structures, count them and compare with the simulations, and then compare with the observation, compare with the simulations, and decide which model is accurate. But while we can, while our simulations become more realistic, our observations is still lacking. We don't have enough observations to constrain our models. So this brings me my second point, and our observational efforts to find these things. So first, I will talk about our efforts around the Milky Way, our own galaxy. So hopefully so far I convinced you that these systems are very important for our understanding of galaxy formation and dark matter. And because of these implications, there's a race right now in the community to discover and characterize these tiny neighbors. And right now, the studies shows that there are, although most of our understanding comes from Milky Way satellites, because they are closer to us, we can better study them, better find them. But there are more than 100 Milky Way satellites still waiting to be discovered. So to address this fundamental issue, we are leading a survey called DELV, Deccan Local Volume Exploration Survey. We started in 2019, and we are using dark energy camera on 4-meter Blanco telescope in Chile. And the goal is basically to cover southern sky with enough depth, observe southern sky with enough depth that we can indeed discover these faintest systems. And guess what? We already started discovering these things. Right now, I am not showing you the pictures of images, these systems, because as I said before, they are invisible images in the images. They are so faint, they only have a handful of stars. But what I can show you is the location of the stars that belongs to a galaxy. So as you can see, this is just the X and Y axis of in the sky, and you can see the stars that are belonging a system, and they are indeed clustering at the center. So we are discovering, and we expect to discover many more. And we recently discovered 6 more DELV detections. These are very exciting times for discovery space. It's really with the our DELV surveys is the current frontier in finding these extremely faint neighbors, our neighbors. Okay, great. When we discover things, then it's not the end of the story, unfortunately. It is just the beginning. After you detect something, then you need to follow up these with better observations. And that's why we are leading a study, a survey with Magellan telescope in Chile. This is a 6.5 meter telescope. It's one of my favorite telescopes. And what we are doing, and this illustrates the power of deep imaging. And as you can see in discovery data, we can only recover like 28 bright star of a dwarf. But then if we get deeper imaging, then we can resolve 25 times fainter stars, which gives us about 900 fainter stars. And now we can start characterizing its luminosity, its size, its shape, and then we can put this newly discovered system in galaxy formation context. So, okay, great. Now we are discovering things with survey. We are following up and getting deeper images and constraining them, characterizing them better. But then we are facing the next big question. Are the Milky Way dwarf galaxies representative? We cannot answer this question by only studying Milky Way dwarfs, right? So we need to go beyond the Milky Way and study other systems and say, how galaxies form in general. So now this brings me to the searches beyond the Milky Way. And here is just the, some of the nearby galaxies, and we are showing what this shows. The red circle represents the local group, which includes Milky Way and Andromeda galaxy M31. And you can see these are the nearby galaxy groups. And as you can see, these are like the closest ones beyond the local group is just like around maybe 3, 4, like 10 million light years away. And it is really a tough thing to do to discover these systems at more distant distance, because even the fainter things at these nearby distances, even the brightest stars of dwarf galaxies appears 300 times fainter. This is familiar. This is similar to what we observe in, like what we experience in normal life, right? The brighter the light, the closer the light is, it's much brighter, and the farther away it gets, the dimmer it gets. So then now it is getting harder to study. The systems are already faint. Now we are putting these into even further away, and it gets even harder to find them. But this is really challenging observationally, but we are doing this. We are doing this with our Pisces survey, and this is panoramic imaging survey of Centaurus and Sculpture. We are again using my favorite telescope, 6.5 meter Magellan telescope, and we are first targeting Cen A. It's a nearby Milky Way sized elliptical galaxy, and then nearest Milky Way analog in complete isolation, NGC 253. And our goal is to just targeting different environments to understand the environmental effects of dwarf galaxy formation. And this is basically showing us the nearby galaxies and their galactic environment. So just to say, if this number, like the value is 0 or negative, this system is isolated. And this shows that the closest galaxies, nearby galaxies, most of them are actually in very dense environments. Only 2 galaxies are very isolated. And interestingly, M94 is very isolated, and it has only 2 classical dwarfs. That's why the study actually who search for dwarf galaxies around this system call it a lonely giant, because it only has 2 dwarf galaxies. In a comparable data, Milky Way and M31 has about 68 dwarf galaxies. So why this galaxy has only 2? Is it because it's living in a very isolated environment, or is it something weird going on with this system? And we can address this by studying even faint, more isolated system, which is NGC 253. So I am leading this survey, and this is this region that we mapped with Magellan, and you can see the galaxy at the center. And in early stage of this survey, we discovered 2 dwarf galaxies, classical dwarfs. And you can see these Magellan images, the individual stars clustered at the center, right? But recently we did another search with the newest data. We discovered 3 more dwarf galaxies around the system, and which made it total 5 dwarf galaxies. And and you can see again, these systems are really faint. You can see a handful of bright stars with some unresolved light. And remember, when you discover a system, the next step is follow up these with better telescopes, deeper imaging. So we already use 6.5 meter telescope to find them. So how we will follow up these systems? So to do this, we use Hubble Space Telescope, and resolve the even fainter stars. And we find actually that these are the first faintest dwarf galaxies confirmed around these are the first ultra-faint dwarf galaxies confirmed around a distant Milky Way-like system. So this opened up a new window to the faintest galaxies in a completely new environment. And interestingly, they are very similar to the dwarf galaxies we observe around the Milky Way. So this points us a universal formation mechanism for these faintest systems. But interestingly, these faintest things, these recently discovered things, are all ultra faint. So in classical regime, we still only have two, just like M94. So this shows a trend for, in isolated systems, we observe fewer dwarf galaxies. Obviously, this is just two systems. We need more systems. We need to map them and understand better. But this is a very exciting era, and we are like opening up new windows to galaxy formation in general. Okay, then another unexplored regime. I have been talking about dwarf galaxies around Milky Way-like systems. What about low mass galaxies? Do dwarf galaxies have their own dwarf galaxies? So in theory, yes. This is again digital universe with called dark matter model, but this time instead of a dark matter halo that will form Milky Way, we are now looking at a clump, smaller clump, dark matter clump that will form a large Magellanic Cloud size galaxy at the center. And you can see the halo is not smooth. There are clumps, there are subhalos, and you can see if you zoom one of them, we can see subhalo within subhalo. We can zoom in more, subhalo within subhalo. And you can see third generation, fourth generation subhalos. This picture shows that even ultra-faint dwarf galaxies should have their own dwarf galaxies. And in observational side, what is interesting is recently discovered systems, and this is like Milky Way at the center, and these dots are just representing the dwarf galaxies orbiting around it. And recently discovered ones are highlighted with green, and most of them are clustering around large and small Magellanic Clouds, which are here. So are they associated with Magellanic Clouds? So maybe, but the fact that Magellanic Clouds lives within the Milky Way halo, it is hard to differentiate which dwarfs are accreted along with a Magellanic Cloud. So one way to address this problem is to look at the isolated dwarf galaxies and check their surrounding and see whether they have dwarf galaxies around them. So this is what we are doing with Meshed Keşke survey. We are using 8.2 meters Subaru telescope in Hawaii and 4.4 meter Blanco telescope in Chile. And we are targeting 11 isolated dwarf galaxies. And our goal is to see the explore dwarf galaxy formation around low mass regime. And guess what? We already detected first dwarfs around dwarfs. This is a dwarf galaxy. This is the size of a large Magellanic Cloud. And we detected a galaxy, we call it Metkeş-1. As you can see in this Subaru imaging, 8-meter telescope imaging, we see individual stars with unresolved light. Another one is discovered around and half Large Magellanic Cloud mass system. So it is even smaller than our neighbor, Large Magellanic Cloud. And it is located here, and we can see the zoom in images, clustered stars. Again, when you first detect, go get a follow-up observation. Since we use 8-meter telescope, now we need Hubble Space Telescope to resolve even fainter stars. And we indeed did that. And we confirmed that these systems are indeed at the same distance with these host galaxies, these nearby galaxies. And they are the faintest dwarf galaxies known around Large Magellanic Cloud mass systems beyond the local group. So again, we opened up a new window into a very unexplored regime. And interestingly, they also are very similar to the dwarfs that we observe around the Milky Way. So again, this points to a universal formation mechanisms for these systems. And we expect to find, we will map 11 systems, we will explore their dwarf systems, and we will hopefully have a better understanding of their formation mechanisms. And then my final point is, what is the future for dwarf galaxy studies? And the future, just a spoiler alert, the future of dwarf galaxy studies is bright, or maybe I should say faint, because faint will be the key to answer some of the biggest question in astronomy. As I just summarized in this talk, like successful wide field searches are already underway, and current frontier telescopes are Blanco, Magellan, and Subaru. But the feature LSST Rubin Observatory Legacy Survey of Space and Time will change the picture. This is a next generation telescope. It is 8.4 meter telescope in Chile, and it will image the entire southern sky every few nights over 10 years. It will create the widest and deepest images of universe, and astronomers are very excited about this telescope because it will resolve billions of faint stars, will open up a new window into invisible universe. Just to illustrate the power of LSST, Rubin Observatory, this is the picture of current efforts. What we are doing right now, we observers are looking at a window, a small window, and we are looking outside and trying to guess the weather outside, right? So if you see this picture, what you will think about it? I would think, okay, it's cloudy, but it is probably nice sunny day, right? But if I get the bigger picture, then I will realize there is actually a tornado in the area. So it is really important to get the big picture. And our current effort is just like this. What we are doing is we are targeting certain regions in the sky, and we are using our powerful telescopes to map this area and to find dwarf galaxies. But what we need is to get the big picture, basically map the sky with the powerful telescopes everywhere. We need to map sky, every point in the sky, and explore it. And LSST will create that, and we are very excited for that. So currently what we are doing is we are targeting nearby galaxies, search their neighborhood. But with LSST, Rubin Observatory, we will be able to find maybe even isolated ultra-faint dwarf galaxies, which will be very exciting because we expect them to have the least effect from normal matter, so they will have a pure laboratory to study dark matter. So my takeaway notes is the faintest and smallest galaxies are unique objects for studies of the dark matter and galaxy formation. Because of their implication, there is a huge community effort to discover and characterize them. And we are leading the current frontier efforts to find dwarf galaxies around the Milky Way and beyond. And future is very faint. And LSSD Rubin Observatory will create the widest and deepest images of universe. And before I end and get questions, I will also advertise this nice documentary by Science Friday. Science Friday did a mini documentary series for women in science, and one of the episodes featured my science, and they call it Galaxy Hunter. I think it's very fitting when we think about what I do. So this is free online. You can just click breakthroughfilms.org and see this incredible scientists doing amazing works. So with that, I can have questions.
Thank you so much. So I have one question that has come in the chat. Firstly, can I just say I love that you have a favorite telescope. That makes me feel very, very good somehow. So we have a question of, are you able to use the James Webb infrared capabilities to observe these fainter galaxies? Does that increase your ability to do some of the science?
Yes, that's a great question. So for finding dwarf galaxies, we need a wide area of sky. So LSSD will be very valuable for that reason. But when we find an object, we need follow-up. And JWST will be crucial for that effort, just like Hubble has been. Similarly, JWST will be crucial for finding, for follow-up studies. But, if JWST happen to point a certain region and find a dwarf galaxy, then it will be incredible. But for systematic search, JWST is not enough because of this field of view, but for follow-up purposes, it will be an incredible instrument for sure.
Perfect, great. Please feel free to put some questions in the chat. So right now, I'll just ask, I've been taking down notes, so I will ask mine. I was sort of wanted to know, what is the threshold that makes a dwarf galaxy from, say, a regular? Like, is there a number of stars? Is there a youth? Is it a question of how young the galaxy is?
So it is really the size and mass of the system, and when you classify galaxies, you look at the first. You try to differentiate them. Right, like how you can differentiate them. One thing, it is spiral, it's shape. You can look at the shape. So that's how like spiral, elliptical, and irregular galaxies are classified. Another way to classify is their sizes. The larger, bigger than Milky Way, and like you can differentiate in that category. But the general consensus in differentiating dwarf galaxies is Large Magellanic Cloud. This is our neighbor, and it is visible with naked eye, so it has been known for centuries. So now we know, when we are differentiating, we are saying that Large Magellanic Cloud, anything fainter than Large Magellanic Cloud is dwarf galaxy. Anything bigger than it, it is, or like relatively larger than a Large Magellanic Cloud, we classify them as galaxies. So it's all about just how we can differentiate, put them into categories so that we can study them systematically.
Yeah. And then I really was fascinated by the way you had the model and then the actual observable universe. And you saw that there were those subhalos that you actually were able to observe galaxies in. But I sort of wanted to ask, your model predicted a lot more subhalos that maybe didn't have observable galaxies there yet. Is that correct? Or did I get the wrong impression? But I was sort of thinking, is it that these haven't formed yet? The light from them hasn't reached us yet, so they could be there. We just don't know that they're there. Is that possible?
So let me clarify something. So what I am showing here, this and this, both are simulations.
Oh, okay.
So it is, we are creating digital universes. What we are looking at in this, the same digital universe. But what we are looking at, this simulation, we are just focusing on dark matter component. What we are looking at here is just the stars and see how things are changing. And this is how, for this digital universe, what we would observe in real life. So as you can see, there are several clumps here, but we don't see them here. The distinction is there is a prediction made here, right? Like, what is the threshold of galaxy formation when the dark matter clump starts to form stars and become a galaxy? So what we need to do now, so you can put different predictions and like create different version of this, right?
Right.
What we can do now, observe real galaxies and compare how many are there, how distributed they are, what is the distribution of them, and compare and constrain the models.
Okay.
But now, to do this, we don't have enough observations. Yeah.
Well, thank you so much. We were almost out of time. If there are any other questions, somebody wants to raise their hand.
I've sent you several in the chat.
Oh, I can't see them.
Okay, I'll mention it.
No. Yeah, no, I saw them here. Okay.
Okay.
Sorry. Can the studies of faint galaxies use crowdsourcing methods, you think?
Crowdsourcing, you mean public efforts? Yes, we are working hard to, especially in LSST era, we will have tons of data. So we will definitely need help with identifying. We are currently asking students to, look through the images and try to find at least the somewhat visible dwarf galaxies. But definitely there is a potential, and we are working very hard to get help from public.
Yeah, I'm sorry, guys. I just saw your questions. There's one more. Any opportunities for citizen scientist projects to be useful here?
Yes, the same answer. Yeah,
yes.
It is like definitely there is a potential, and we are working hard to create these projects and make it available to public so they can help us in these efforts, because as you can see, implications are huge and it is so many data. We just need help from everyone. Yeah. So
you have a favorite telescope, but I wanted to ask, is Burçin's galaxy your favorite galaxy then? Because you do have a namesake galaxy.
Yeah, that's true. Yeah, I guess that it must be, right?
Yes.
Since everyone now knows me with that galaxy with very rare. So it is not a dwarf galaxy. It's completely new type, different type of galaxy. These things are actually, dwarf galaxies are the most numerous galaxies in the universe. But since they are faint and small, it's hard to find them and study them. And Burçin's galaxy is a extremely rare galaxy, and it's very unique. It's a ring galaxy. It's like a Milky Way size system. So I gave a TED talk about it. It's just 5 minutes. If you are interested, you can just check it out. It's really cool.
Yeah, so we'll absolutely feel free to put it in the chat, and then we'll send it out to everybody who's come. But we are out of time. We could listen to you all day. So thank you so much, Dr. Pakdil. I can, yeah.
I know I opened it, but where it went is a good question.
Yeah, I'll do it. I'll put it in.
Okay, thank you. All right.
So I've just put in a link in the chat. That's our survey data. We would love for you to fill that out. That really helps us when we go to apply for a grant to keep Roger that going. So thank you very much. Thank you all for coming.
And we'll be picking up in just 9 minutes now.
Okay.
Thank you.